All right, well, let's get started. We're going to talk about today the in a little bit more detail. We're going to talk about potassium and then some of the other macro and micronutrients. So I've got about 28 slides. I usually figure about a minute per slide. So we should breeze through this pretty fast. But if you do have any questions, by all means, stop me and let me know. Okay, let's start with potassium. Okay, potassium is K, and we established just the other day that K is also called potash. All right, potash. Now, the beauty of potassium in the soil is that it's kind of a loner. If you remember yesterday, we talked about how some things are mobile and some things are immobile. And specifically, we talked about phosphorus and how it's the marrying kind. It likes to get hitched up with something. The beauty of potassium is that it likes to just be a loner. And so it's just this K plus cation that floats around in the soil. Because it is positively charged, that does mean, however, that it will attach to clay particles and other negatively charged colloids. So that is a consideration as well. It's not easily lost to the atmosphere. So remember when we talked about nitrogen cycling, and we can get nitrogen that gases off as either ammonia versus ammonia volatilization, or it can be denitrified and gassed off as N2O or some other nitrous oxide gas. Potassium does not do that, and so it'll stick around in the soil for quite a while and be available for plants to use. Actually, one of the simplest nutrients that we manage is potassium. Okay, influenced a lot by the CEC and also weathering. We'll talk about the weathering in just a little bit. We oftentimes worry about nutrients being removed from the soil. We've talked about how nitrate leaching and getting nitrate into the groundwater is bad. If we get phosphorus into surface water, that's even worse. The beauty of potassium is that if we get that stuff into water or into groundwater, it generally is kind of a nothing burger. So we don't have a lot of environmental concerns because of potassium. And in fact, we can get soil potassium levels that are super high, and it generally doesn't cause any negative effects to crops. Okay. Did we look at any potassium deficiency symptoms last time? Okay, remember there's four nutrients that are mobile inside the plant, right? They are N, P, K, and magnesium, okay? So if we're looking at a potassium deficiency, where, Madison, are we going to find that deficiency symptom?
Can you hear me now?
Yes,
Okay.
We didn't give up on you.
Would it be at the top, or I would want to say the top of the plant, but we also talked about the middle of the plant, so I'm kind of...
Okay, if potassium is mobile, remember that it can steal stuff from the older tissue and move towards the top.
The deficiency top.
Yep, so you're right. It's going to show up actually in the bottom of the plant. And I've got just a couple of pictures here. They're not actually very good. We're going to cover all this stuff, so hold on tight. Okay, on the left, this is a soybean crop, and black and white, old picture. I really need to update these. And then on the right, we can actually get some speckling that'll happen in alfalfa. Well, that's not alfalfa, it's hairy veg, same family, right? So we can get some speckling that'll happen. with potassium deficiency. But a lot of the times what we'll see is with potassium deficiency, the leaf margins will turn yellow first. You know, you can kind of see how it diffuses into the middle of the vein here. And so with potassium, it generally happens on the leaf edges, and then we'll move in from there. You can see how this is happening on leaf edges. All right. Now, we won't be surprised to find out that, you know, nitrogen has a cycle, right? Well, so does every other element that we deal with in plant nutrition. So potassium also has a cycle. And it really doesn't look too different from nitrogen. There are a few key differences, though. Number one, we don't necessarily have plants that fix potassium. If we have a plant growing up here and it dies, it will put potassium back into the soil, but it's not potassium that came out of the air. It's potassium that it derived from the soil to begin with. And so this is just the cycling right here. We're not creating any new potassium. It's just being recycled, okay? We have stuff that lives in solution, okay? And the plant can use that. But that is in equilibrium with what is exchangeable. So this is stuff that lives on clay particles. That is also in equilibrium with what lives inside the clay particles. So it can give and take. And we've got these primary minerals that are basically sources of potassium in the soil. Okay, we can have losses because of leaching, absolutely. We don't normally think of potassium leaching because it's positively charged and it's attracted to clay particles. But like you guys know, if something that is negatively charged leaches, something that's positively charged has to go with it. So we can lose potassium via leaching. It can be lost via erosion or runoff. Okay, so this is the potassium cycle. Now, if we look at this in terms of what's available in the soil and what's going to happen in the plant, what you're looking at here is soil potassium. And as that increases, we have basically a relative yield increase, okay? Duh, right? Plants need potassium to live, and if they have more of it, then they're going to live better. But this dashed line right here is what we call sufficiency level, okay? And a plant will actually consume potassium beyond what it needs, and this is what we call luxury consumption. And the potassium content in the plant will actually keep going up. So we really don't want this, you know, we don't want the plants taking up extra potassium because for one thing, they don't need it. And another thing is that unless we're recycling the plant back into the system, it's just going to get harvested off the field, okay? All right, now soil minerals are contributors to the potassium in the soil. And so what you're looking at here is we've got kaolinite, which we know is a 1-to-1 clay particle. So it's kind of a mix. And then we have a smectite, which is a 2-to-1 type clay. And what we do is we go in there and we measure total potassium, exchangeable potassium, and then water-soluble potassium. Now, guys, I've raved about this all year. Water-soluble potassium. Look at this. Whoops, let me go back. 2, 5, and 4. That's parts per million. So is our water doing a very good job of stripping the potassium? No. Very good. Now, if we measure exchangeable potassium, so this is what is living on the cation exchange sites, we're not surprised to find that our kaolinite is very low compared to a mix or a smectite type clay. The reason being is that this is a 1-to-1 clay and the CEC is lower. Okay, so we can't have nearly as much potassium on a kaolinite as we do on a smectite. And then if we measure the total potassium, look at these numbers, they're quite a bit larger, right? So Garrett, what does that tell you about the form of potassium in the soil?
I don't know.
Anyone want to butt in here? Wade, do you have any idea? Why would we have so much total potassium and so little exchangeable and water-soluble potassium?
Could it be that the potassium isn't usable?
That's exactly
Very
right.
little.
Yep. This potassium right here is basically part of the clay mineralogy. Okay. And a plant can't get at that. And so actually there's not very much of it, of the total, that the plant can actually get at. All right. The way this kind of works is if we look at weathering, let's say we start out with something like a mica, and as we move from left to right and end up with something like a vermiculite, these little black dots in here, that is our total potassium, okay? If we went in here and we measured this, you know, we might have a total potassium number of, let's just say 10,000. If we measured the water-soluble potassium and the exchangeable potassium here, they're both going to be very low because this stuff is tight, pinched in here, plant can't get at. But as these things weather, what happens is we get something like a calcium that'll come in and it'll cause these clay layers to kind of cleave apart. And when it does that, it exposes some of these other potassiums, okay? And now, if we were to measure, again, total potassium, it's probably going to be the same, but our water-soluble and our exchangeable potassium are going to be much higher because now we can get in here and strip these guys off. And as we weather to an illite and to a vermiculite, again, the water-soluble and the exchangeable amount of potassium is only going to increase. Now, having said that, what can happen is if these soils get extremely dry, we could actually go backwards, okay? So these guys are hydrated. That's what these little bubbles around the cations means. They're hydrated. And so if we dry out and we go the other way, we can actually kind of reverse weather these clay particles and our potassium becomes unavailable again. So clay mineralogy plays a huge role. Let me tell you a little bit about geography. Oh, gosh, I'm tired. I'm just boring the crap out of myself too. Let me pull up a map here. All right, let's find the basin here. Potassium concentration in the basin is very largely influenced by location, all right? So about the time you head east out of Moses Lake, so let's say Wheeler and to the east, potassium concentrations in the soil increase by quite a bit, okay? So we might have potassium numbers, especially out in this dryland area out here, in the 3, 4, 5, 6, 7, 800 part per million range out here, okay? And the reason being is that we tend to have more clay and less sand out here, okay? And that is causing, it's potassium that's in that weathered clay and it's available for plants. So a lot of guys out here that farm never ever have to apply potassium because there's just a lot of it. Now, as we head this way, out in this region, we're getting more and more, so Quincy, Dodson Road area, we're getting into really sandy soil, okay? And sandy soil is basically inert, and it doesn't contain or have a lot of potassium in the clay particles. And so out here, potassium numbers are 150, 100, sometimes 80 parts per million. Okay, so very low. And the same thing can be said for Royal City, Mattawa area. These Mattawa soils tend to be really sandy. We might see them into the 50s, 60s, so very, very, very low. All right, let's go back here. Okay, so you won't be surprised to hear that in areas where we grow crops, we quite often have to apply potassium fertilizer. But there are soils that have the capacity to supply their own. Okay, let's move on to calcium. Okay, yesterday I told you that calcium is an important part of cell structure, plant turgidity, and for animals, we know that our bones and our teeth come from calcium. And so it's an important part of biology in both plants and humans. This is kind of an interesting sidebar. African soils tend to have a lot of calcium in them. And so they kind of postulate that some of the large species of mammals on the earth live in Africa and are adapted to Africa because the soil has a lot of calcium and they can grow these big bones and tusks and other things. So that's just kind of an interesting sidebar. Okay, calcium is absolutely important for root development. What you're looking at here is two hydroponic solutions. The one on the left, the plant was grown in an absence of calcium. And on the right, everything was identical except they added calcium to the nutrient solution. And so you can see calcium is important in plant growth. Did I mention that everything has a cycle, right? So calcium also has a cycle. It's actually very similar to potassium, which is similar to magnesium, in that a lot of the calcium lives on exchangeable surfaces. There is some in solution, and it can exist in 2-to-1 clays. And really everything else is about the same, right? We've got minerals, let me go back, minerals that weather and contribute to the soil solution calcium. We've got mineralization where organic matter is broken down and that calcium or magnesium can go into solution. The bugs can take it up. This all looks really familiar, right? I think we all understand pretty well how this cycling works. Okay, magnesium. I don't have a lot to add here other than it's not needed or it's not present in quite the same amount that calcium is. And generally, when we add either calcium or magnesium, because our crops need it, is because our pH gets really low. Okay, around here, adding calcium and magnesium as fertilizer is pretty rare. And usually we're doing it to address a pH problem rather than a calcium deficiency. So generally the way I do it and the way my philosophy works is that if we're managing our pH appropriately, that these guys kind of take care of themselves. All right, micronutrients. We need to talk about deficiency versus toxicity because with micronutrients, this is a big deal, okay? There's usually a pretty thin line between having enough of the nutrient and having too much and causing problems. So we'll talk about that in addition to some other things. All right, so if we look at the concentration in the soil as a function of plant growth, okay, as we increase the concentration in the soil, our plant growth is going to go up to a point, and right at this point is what we call our sufficiency level, okay? the concentration can increase, but our plant growth will not necessarily increase with that. So we kind of want to get right to the edge of this plateau, because beyond that is where we can cause problems, all right? Now, as our concentration in the soil increases, our plant growth or yield decreases, and this is what we call toxicity. A huge potential problem, especially with the micronutrients, and let me tell you why. This is when we look at tissue levels of different micronutrients, okay? What we're looking at here is if it's white or deficient, and if it's this dark color of blue, it's toxic. And so look at this range of all these micronutrients between what's deficient and what's toxic. Look at boron. So if we're running like at a 10 part per million level in boron, by the time we get about to 100, we're going to start to see toxicity problems, okay? Our plants absolutely need boron to grow, but too much of it and we cause problems very, very quickly. Okay, here's a table that shows you kind of in detail the functions of all these things. This is a good reference to have, but I'm not going to ask you about this on any test. We talked about molybdenum yesterday being important for nitrogen fixation. We talked about how zinc is important for enzyme activation, things like that. So, yeah, you don't really need to know too much of this stuff, but you know where the reference is in case someone asks you, right? All right. In addition to helping with plant growth, a few micronutrients have the ability to help with disease problems, okay? And basically what this table is showing us here is what they did is they took cowpeas and they added various levels of manganese and then measured some incidence of disease. And you can see that when they didn't apply any manganese versus various levels of manganese, their incidence of disease dropped pretty significantly. So just keep in mind that when we add micronutrients, there may be other benefits that come from it as well. I'm not saying this is going to happen on every crop, but in this case, with this crop and this particular disease, it seemed to have a positive effect. Okay, this is the micronutrient cycle, okay? And for this one, I'm not showing it as any specific micronutrient. One thing that I want to point out that makes this especially complicated is this word right here, chelate. I'm going to talk about that in just a minute. These micronutrients generally don't exist very much in solution. If they do, it's a very small amount. The plant can use what's in solution, obviously, but in the case of micronutrients, they can also use this chelated version. And again, we'll talk about what chelation is in just a minute. Okay, we know this. Soil pH is a huge factor in micronutrient availability. I believe we talked about this when we talked pH. Okay, most of the micronutrients increase in availability as pH goes down. So lower pH means higher availability. The only exception to that is molybdenum, okay? It tends to be more available as the pH increases. All right, this right here is chelate, okay? Chelate comes from the Greek word for, let me see if I can make a whiteboard here. From that word, chelis, and to us Americans, that means claw. And the way this is supposed to work, let me get rid of this guy, is if you were to look at these things under a microscope and look at my camera right now, they kind of look like this, where you have this big, ugly organic molecule up here. And then there's two, what they call, it's basically a tooth. This is the claw portion of the chelate. Anyway, this claw portion right here just happens to be, just happens to be the perfect size to hold a micronutrient. So in this case, it's an iron. This one too is for iron, but it could be manganese, copper, or zinc, okay? And the beauty of this organic structure right here is it holds that micronutrient and allows it so that it doesn't become some kind of insoluble mineral. So micronutrients can combine with carbonates, and when it does that, it basically turns into a rock that the plant cannot use. And so a chelate holds it in this form that is plant available. When we do extractions for micronutrients in the lab, we actually use chelates to extract that iron, manganese, zinc, copper, and that's how we do the test in the laboratory. EDTA stands for ethylene diamine tetraacetic acid. EDTA. Don't need to know that. That's just fun to say.
Oh, you're not screen sharing the PowerPoint if you are meaning to.
Okay. Thought I was. Bam. Okay, here's our chelate right here. So we got this, it's showing up now, right?
Yes.
Okay. Here's our big, ugly organic molecule. Here's the teeth that are latching onto this iron in an electrostatic attraction that the plant can get at. So this one is EDTA, and this one is another, it's kind of a sugar or gluconate form. Anybody go to the store and buy pills that say like calcium chelate on them? You guys are young enough. Maybe your grandma does. But when you go to your grandma's house next time, look in her cupboard. She probably has like some chelated calcium, something or other in her cupboard. Basically, you're buying like an organic molecule with instead of a micronutrient, it's a calcium right here. And it's supposed to help the body absorb it much faster. Okay. Here's some other ones, but I'm not going to really talk about them very much. We've talked about molybdenum. We talked about boron. We looked at some chlorine deficiencies yesterday, so I don't have very much there. Okay. All right. So remember that depending on what nutrient we're talking about, its life cycle and processes in the soil are different, right? So for these guys, they're largely affected by cation exchange. Some of these other ones, we know that the soil biology plays a huge role in making them available. And with things like iron, manganese, and zinc, these are, we like to get these into a chelated form, and the pH affects their solubility quite a bit. We can have deficiencies. And micronutrients actually, when we add them to the soil, tend to be a little bit more expensive. But I think most people are usually willing to put on a micronutrient so that they can just kind of avoid negative effects from having micronutrient deficiencies. Okay, we've got to be careful that what we add isn't in an amount that's so much that will cause toxicity. Wow, a lot of conclusions here. Excess of nitrogen and P is really bad in the environment. So usually when Uncle Sam comes out with his regulator guys, they're usually looking for nitrogen and phosphorus. Copper can be poisonous, especially if it gets in the water. The fish don't like it. In fact, they'll usually put copper in the canals to kind of keep the algae and crap like that from growing too much. I don't know. I went swimming in the canal last year and I turned out okay. Maybe I've got some twitches or something, but I did it my whole life. That's it. Any questions about those nutrients?
You said that too much can be bad for the soil. So how would you get rid of that excess amount?
Yeah, that's a really good question. So it depends on the nutrient, okay? For things like nitrogen, a lot of the times we get rid of it by leaching it out of the soil. And but that's bad too, right? Because then it gets into the groundwater and can cause problems. If it's something like phosphorus, we can't leach it very well because it's very immobile in the soil. And so what we try to do, number one, is we try not to add any more. And number two, we try to grow crops that will take up large amounts of that nutrient. And so, and then harvest it. So one of the common things to do is to grow alfalfa on a soil that has maybe too much phosphorus. And then year after year, growing that alfalfa, harvesting the material off, we're basically mining off that phosphorus. So that's another way to do it. Yet another way is to adjust the pH. So if we've got a micronutrient that's available in too high of an amount, if we adjust the pH up, it'll cause it to be less soluble. It's still there, right? It's just not as soluble for the plants and won't cause as many problems. So yeah, it really depends on the nutrient that we're working with. But good question. Any others? Okay, let's sign off here. You guys have a good weekend. We'll be back on the Zoom on Monday, and we'll have lab on Tuesday. We're going to talk about phosphorus on Monday. Phosphorus is kind of my baby, and so we're going to like get down to the nitty gritty, like Nacho Libre says. Okay, we'll see you on Monday.